Hello, I welcome you all to this another interesting screencast. The problem reads: determine the angles theta for equilibrium of the 4 pounds disc using the principle of virtual work. Neglect the weight of the rod. The spring is unstretched when theta is equal to 0 degrees and always remains in the vertical position due to the roller guide. And we're assuming there is no friction at the roller guide and this contact surface. All right. This problem is coming from the Engineering Mechanics and Statics textbook, 13th edition by R.C. Hibbeler. So we have been told to use the virtual work method, and this is an alternative to the equations of equilibrium methods for a particle, for a rigid body, for interconnected rigid bodies. So if it is an alternative, it means we can solve this particular problem using the equations of equilibrium for a rigid body. Alright, but in this particular case, we're going to solve this using virtual work method. So what is this method? The method states that the total work in a system, in our system, this system which is a rigid body, is the total virtual work is equal to 0. And this virtual work is due to, it can be due to the product of a force and translational virtual displacement. It can also be due to the product of a couple moment and rotational virtual displacement del theta. And when we sum up all these virtual works in our system is equal to 0. So given a force and a virtual translational displacement del r, for virtual work to exist, the two must be collinear or parallel. And if they're in the same direction, we have a positive virtual work, otherwise we have negative. Same applies to a couple moment m and the rotational virtual displacement del theta. The two must be collinear or parallel, and if they're in the same direction, we have a positive virtual work, otherwise we have negative. So in a nutshell, this is what virtual work is. Alright, so first things first, we draw the free body diagram. We have a hinge at A there. So we expect two reaction forces in the vertical direction like so, and in the horizontal direction like so. Okay. And then we have the weight there for the disc. And then let's do a section of this spring. We are going to have in this particular spring a spring force Fs. Okay, so let's label this. So this is Fs, this is Fs, and this is By. All right, and this is Bx, and this is W. All right. So now let's apply vector displacement. I'll apply a vector displacement. Let me apply it at A. You can apply it at A, you can apply it at C, you can apply it at B. At B, you can apply a rotational vector displacement. So let me apply a translational vector displacement at A, and let me apply it in this direction. Okay, in that direction, going down. See, my arrow is pointing going down like so. Great. So let me draw the deflected configuration of this system. So we are going to have something like so, right? So what happens? This point is going down at A. What happens at C? At C, you expect it to be going up, right? Of course. So that's we expect it to go up like that. Okay. And at B we have a what? Anti-clockwise. We have this movement, right? Anti-clockwise, counterclockwise, vector rotation or vector displacement, right? In that order, like so. Okay, we have this movement. All right, let me delete it to it's just tightening my, just adding more lines. It's making my work untidy. So right, we've done this. Okay, and the points where we expect vector work to take place is at A and C. Why? Because we have both the translational vector displacement and the forces, and both are what? Collinear or parallel. All right. Okay, great. At B, we only have rotational vector displacement. We do not have translational. Rotational vector displacement goes with a couple moment. Translational vector displacement goes with a what? A translational force for vector work to exist, right? Great. So once we've done this, we are going to pick our fixed reference as B. So let B be our fixed reference. All right. So if that is the case, then let's define it. Let's define it quickly so that we start working. All right, let's define point C, reference. Okay, let's define point C, this point there, like so. This point, right? Point C with respect to point A. Point C with respect to point B rather, okay? So we want to define this height. It looks too small. It is too small, of course. So this one. So this height, because the change is in the y, so we are interested in the height. So we are going to call this as our yc. Okay, this is yc. And let's define this other one there. Okay, we pick a guide that will make this line straight. Okay, so this one, and then with respect to A, right? There we go. So this one we are going to call it, again we are interested in the y. Okay, we'll call this one as YA. Okay, in fact it's del okay, YA. Then this one there, this vector displacement, we'll call them del YC, and then this one will be del YA. Okay, all right. So W is given already. We've been told W is 4 pounds. Fs, which is the spring force, is equal to K, which is the spring constant times the stretch. K is given as equal to 50 pounds per feet. S is equal to L final minus L naught. L final, L naught is equal to, say, equal to 0 foot at theta equal to 0 degrees. L final is just going to be equal to 1 sine theta, okay, which is just basically equal to sine theta. Okay, it's like this, right? Like this. This is the distance that we want, okay, which is YC. We have the angle there, and this length been told is 1 foot. Okay, so how do we find this? This is sine 1 sine theta, okay, which is just equal to sine theta. All right, this is the one here. Okay, great. Therefore, the spring force Fs is just equal to 50 times L final, which is sine theta minus 0, and this just gives us a 50 sine theta. Then we have YC. YC is just equal to sine theta. Therefore, the vector displacement there, del YC will just be equal to cos theta del theta. YA is just equal to 3 sine theta. Vector displacement there, del YA will just be equal to 3 cos theta del theta. Then we have the virtual work equation del U equal to 0. At A, we expect to have positive virtual work because both the virtual displacement and the force, which is the weight, are in the same direction. So we say W times del YA positive. At B, we don't have, at B, we will not have any virtual work. Why? Because we do not have any translation or virtual displacement. Okay. 2, we do not have, so we have the translation of forces but no translation of virtual displacement. We have rotation of virtual displacement here but no couple moment, therefore no work on either side, no work at B. At C, we'll have work. The virtual displacement is in the opposite direction of the spring force, so this will have a minus Fs times del YC, and that's about it. We sum up everything. This is what we have. So this is equal to 0. So let's replace the values, this del YC and values of the forces. So W, we said, is given is a 4. W is a 4. And then we have del YA. Del YA is 3 cos theta del theta. Then we have minus Fs. We said is 50 sine theta. And then we have del YC is cos theta del theta. Okay. Can this we do like so? Then this is equal to 0. Right, so let's write this. So this will be equal to factor out del theta. Then we'll have a 12 cos theta minus 50. This is 50 sin theta cos theta, then equal to 0. We know that del theta is not going to be equal to 0. The only part that to be equal to 0 is this. We can write this as cos theta 12 minus 50 sin theta equal to 0. So we have cos theta equal to 0. We have cos theta equal to 0. We have also sin theta equal to 12 divided by 50. Okay, so in one case we have theta equal to 90 degrees. In the other case we have theta equal to, that's 12 divided by 50, cos inverse of that gives us, 12 divided by 50 sine inverse of that gives us 13.89 degrees. Okay, so I think that is about it. We have found the solutions to this particular problem, and I hope this video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.